Hey there, welcome to this video on transforming to linearity and weighted least square WLS. Have you ever tried using linear regression and found that it just didn't work well? Maybe your prediction were off or the error were getting bigger for higher values. That's because real world data does not always follow a perfect straight line pattern. But don't worry, today we are going to fix that. We will talk about two super useful techniques. The first one is transforming data. This helps when data is curved instead of linear. And the second one is weighted least square WLS. This helps when error margins aren't consistent. By the end of this session, you will know exactly when and how to use these techniques. And I will even show you how to apply them in Python. So grab a notebook, get comfortable, and let's get started. All right, before we get into the technical stuff, let's first ask, why does this even matter? If you have ever used linear regression, you know that it assumes a nice straight line relationship between variables. But here's the thing, real world data is messy. Take house price as an example. A small apartment might cost $50,000, but a luxury mansion could cost you up to $5 million. The price does not just increase in a straight line, it grows exponentially. If we use a regular regression model here, it won't capture this trend correctly. Or think about salaries. Entry level jobs have similar pay, but as experience grows, salaries vary a lot. If we assume a simple linear pattern, we will miss the variation and make bad predictions. So, what's the solution? The first technique, transformation, which helps when the relationship is not a straight line, and weighted least square WLS helps when error margins change across data points. By learning these two techniques, you will be able to make more accurate prediction and better regression model. Before we jump into solutions, let's quickly refresh how linear regression works. The basic formula is y equal to beta naught plus beta 1x plus epsilon. Here's what each part means. Y is what we are predicting, like house price. X is the predictor, like house size. Beta naught is the starting point, like intercept. Beta 1 is the slope, how much y changes when x increases. And epsilon is the error, that may be random stuff that the model can't explain. Now, this formula only works well if the relationship is actually linear, but what if it isn't? Let's say we are predicting stock prices, they don't move in a straight line. Or what if we are analyzing population growth? It's usually exponential. So this is where transformation come in. They help reshape the data so that regression works properly. And what if the errors aren't stable? That's where WLS saves the day by handling situation where errors change depending on X values. Bottom line, if your data isn't behaving, we have got tools to fix it. All right, so we know the transformation help when data isn't linear, but what kind of transformation can we use? Here are four most useful ones. The first one is log transformation, great for data that grows exponentially, like stock prices or population growth. It smooths out extreme values, making the trend easier to model. Now, the second one is square root transformation. Used when data has increasing variance as values get bigger, often applied in count data like website visitors per day. The third one is reciprocal transformation. Works well for inverse relationship like speed versus travel time. If y decreases rapidly as x increases, this is a good choice. Now the fourth one is polynomial transformation. If the trend is curved, adding x square or x cube helps capture the shape. So transformation are basically tricks to reshape data so that a linear regression model can handle it better. So previously we just discussed how many types of transformation is there. Now in this slide we are going to discuss about what is the transformation process. Now, so how do we actually transform data? The first step is visualize the relationship, plot a scatter plot to identify whether the data follows a straight line pattern or is curved. Now choose the appropriate transformation. Identify whether log, square root, inverse, or polynomial transformation is best suited. Now apply the transformation to x or y or both. This alters the data set so it follows a linear trend. Fit a regression model on the transformed data. Now in this step, run linear regression again and analyze the new result. Now finally, check residuals for improvement. If the transformed model produces randomly distributed residuals with constant variance, the transformation was successful. If not, consider trying a different transformation. Transforming data before regression ensures the model is well suited for prediction, reducing error, and improving accuracy. Now this is the next slide of transformation process. Here we can see various steps. In the step one, what we are seeing is our original non-linear data, and in step two there is log transformation, square root transformation in step 3, reciprocal transformation in step 4, polynomial transformation in step 5, and in step 6 there is finally residual analysis after transformation. So this was all about transformation process. Now we need to know about what is residuals. So now let's talk about residuals. They help us understand if our model is working properly. Residuals are simply the difference between what the model predicted and what actually happened. Residual equal to actual value minus predicted value. In a perfect world, residuals should be randomly scattered. But if we see a pattern like residuals getting bigger as x increases, that means something is off. This issue is called heteroscedasticity. Fancy word, I know. It means that as x get larger, the errors keep growing. For example, predicting salaries. Entry-level salaries have small variation. Executive salaries have huge variation. A standard regression model won't know how to handle this. This is where weighted least squares WLS comes in. It reduces the impact of large errors by giving them smaller weights. This keeps our model stable and reliable. Alright, now let's talk about a big issue in regression that many people overlook, heteroscedasticity. Yeah, it's a long word, but don't worry, I will break it down in a way that makes total sense. So in a perfect regression model, we assume that errors are evenly spread out across all values of x. This is called homoscedasticity, fancy term, but it just means that errors are consistent. But in real life, that's rarely the case. Often as x increases, the error grows bigger too. This is called heteroscedasticity, which basically means unequal spread of errors, and this is a huge problem because it make our prediction less reliable. For example, let's say we are predicting salaries based on years of experience. Entry level salaries pretty close together, high income salaries huge variation. Some people make 100k, some make 500k. A normal regression model treats all points equally, which means it struggles with this huge variation. That's where weighted least square WLS comes in. It reduces the influence of high error points, making the model more stable. So if your data has growing error margins, WLS is going to be your best friend. Alright, now that we know that heteroscedasticity is, how do we know if we need WLS? Here is a 3-step checklist. Now step 1, check the residual plot. A residual plot shows how errors behave. If the errors spread out as x increases, you have heteroscedasticity. If they stayed evenly scattered, you are fine. Step 2, run a statistical test. There are tests like Bruce-Pagan test and white test that mathematically confirm if your error variance is changing. If they say yes, you need WLS. Step 3, think about your data. Certain data set naturally have increasing variance. House prices, for example, expensive homes have unpredictable prices. Salary prediction, high earners have bigger variation. Stock market trends, large companies have massive fluctuation. If you see increasing variability in your data, WLS is the way to go. It helps make sure that our model is unfairly influenced by large errors and remains stable, reliable, and accurate. Okay, now let's go step by step and see how WLS actually works. It's all about assigning different weights to different data points. So the step 1 is run a standard regression OLS. First, we apply ordinary least square OLS and check if errors increase with X. If yes, we move on to WLS. Step number 2, assign weights. Instead of treating all data points equally, we adjust their importance. The formula for assigning weights is Wi equal to 1 divided by variance I to the power 2. Now here a large errors equals to smaller weights which have less influence, and smaller errors equal to larger weights which have more influence. Now moving to the another step, step number 3, rerun regression with new weights. Now we fit the regression model again, but this time it takes this weight into account. This ensures that big errors does not distort the prediction. Now, step 4, check the new residual plot. If WLS work, the new residual plot should show that errors are evenly spread out, meaning we have successfully fixed heteroscedasticity. Think of it like grading a student performance. Final exam matter more than homework, right? WLS does the same thing. It gives more weight to reliable data point and reduces the influence of noisy data. Now here's the main and final part in which we have implemented WLS in Python through code. Here below you can see the code, and uh, we have explained the various step through the code and using comments. So it's very much simple to understand, and if you want to implement it, you can do it by yourself too. uh, this is all about implementation part. And that's the wrap. We covered some powerful techniques today that will help you build better regression models. And by the way, huge shout out goes to Bishnu Upadhyay and Sonu for making this PowerPoint, and huge shout out to myself to make this for making this video. And thank you so much for watching. If you still have questions, feel free to ask in the comments. See you in the next video. Happy coding. Bye guys.